Welcome back. On this video, we will talk about confidence intervals again. And in the first part of these two parts confidence interval video series, we talked about the theoretical framework behind this topic, and you will find the link in the description. But on this video, we'll make an example using AnyLogic in order to understand how to apply confidence interval in any of your AnyLogic models. Second, we'll understand some of the features AnyLogic has to work with confidence intervals. And third, we will explain how to use confidence intervals to explain your results to your stakeholders, who can be your client, your supervisor, or anyone who is interested in what you're doing. So let's get started.
So for our example, we have a very simple simulation model with a simple process. We can take as an example some kind of service system where the agents or the customers will enter the process, will go through a delay. This could be some sort of paperwork that they have to fill. And then this is followed by two consecutive services. These customers are serviced by a group of attendants. In our case, they are five. The customers are only willing to wait a certain amount of time to be serviced, and this is why if a person waits too long, they will just leave the system without continuing with the process. Now, to provide variability to our model, all the delay times and the delay and the surfaces are indicated with certain distributions, as well as the time that the customers are willing to wait before they leave the system. So this is why our model is stochastic. Now, the aim of the simple process is to find the number of customers that will leave the system before being serviced. For that, we have added this variable, which will be added progressively every time a customer leaves the system. So because of the variability that currently exists in the model, we expect that every time we run the model, we will get a different number for the number of people or number of customers that leave the system. So we are going to see that now. The model is going to run for one working day, and at the end, we are going to use this button to trace the number of people who leave. So we run the model and speed things up, and you can see that at the end, we have 27 customers who left in this working day. Now, if we run the model again, we should get another value. But surprisingly, we got the same value. So let's run it a third time just to make sure. So again, we are getting the same result. So why is that? Well, actually, there's a very simple reason for this, which is the fact that we have a fixed seed chosen. So although our model is stochastic, but because we have chosen a fixed seed, this means that every time we run the model, AnyLogic is going to choose the same values out of all the distributions that we have specified, and this is why we are getting the same result. So this is something that we have to be careful about. A fixed seed is useful for the verification of our model, but if we want to see the actual variability, we will need to specify a random seed. So this means that now every time we run the model, we should get a new result because every time the values that are going to be chosen from the distributions are going to be new or different. So let's see this now. Now that we have chosen a random seed, let's run the model. So now we have actually gotten a new value, even different from the one we were getting before. So I will also run the model again for a second time. So now we also got a new value, also one more time, also a new value. So of course you get the point. If we run the model for 100 or even 1000 times, we should expect that every time we will get a different value. Of course, some of the values will repeat at certain time, but this is the general idea. So the idea is that we need to run our simulation model for a certain number of times until we reach a reliable value for our variable. Fortunately, we don't have to do this manually because there is a built-in experiment in AnyLogic that allows to do that automatically. This experiment is called the Monte Carlo experiment. Now, by definition, a Monte Carlo simulation is used to model the probability of different outcomes in a process that cannot easily be predicted due to the intervention of random variables. So, it is a technique used to understand the impact of risk and uncertainty in a certain system. So, this is exactly what we need. So what this experiment does is that it runs the model several times or a certain number of times while changing the values of the random variables, and then it gives an estimate of the needed variable or the needed outcome based on these runs. Now, if you are using the PLE version of AnyLogic, you are not capable of using the Monte Carlo experiment. However, you can easily replicate it using the parameter variation experiment, and this is what we are going to see now. Now, in order to be able to use this experiment in AnyLogic, we will need to have at least one parameter in our model. And this is why we simply replace the values in one of the distributions with parameters. Now, as you can see, there are two options in the experiment, the varied in range and the free form. We are going to use the free form option in the experiment because this is the one relevant to the Monte Carlo simulation. The other option is used for different situations that we are not going to talk about in this specific video. Now, AnyLogic provides you with the capability of specifying the number of runs that you need your model to run, and also gives you the ability to use replications. Now, you can read more about the issue of replications in AnyLogic documentation. However, the only thing that you should know now is that you can specify the total number of times that you want your model to run or to repeat here. So let's say 10 times. This means that the model is going to run for 10 times without using any replications. Or the other option is that you can specify here one run and use replications for 10 times. So both cases are exactly the same in our situation. Of course, as mentioned earlier, we should not forget to specify a random seed. And here in the Java action, we can specify anything that we need to do before or after an experiment. So what we did here is we added some code in order to export the value of the variable that we are looking for after each experiment run. So the Excel sheet that we will get is going to look something like this. So this is the value of the number of people who left after each simulation run. Now, since the value that we are looking for is actually the number of times or the minimum number of times that we need to run our model in order to reach a certain confidence level, then this means that what we need to do is to choose our confidence level. And then we need to go through several iterations until we reach the needed number of runs that provides us with an acceptable margin of error. So this is a reminder that these are the formulas that we are going to use. So we are going to specify a certain number of runs or iterations. And of course, we will need to choose our confidence level. And based on that, we are going to calculate the margin of error. And we will see if the margin of error that we are going to reach is acceptable to us. In case it is, then this means that the number that we have chosen for the replications or the number of runs is satisfactory. In case the margin of error is not acceptable to us, this means that we will need to increase the number of runs gradually until we reach a margin of error that we are willing to accept. So we will run our parameter variation experiment, which we have made to replicate a Monte Carlo experiment. And when the experiment finishes running, all the results will be exported to the Excel sheet as already mentioned earlier. These are the exported results. As you can see, we have 5 results relevant to 5 simulation runs. Now here, I have prepared the calculation for the margin of error in order to see if it is satisfactory to us. So this is where the average is calculated of these 5 values. This is where the standard deviation is calculated. This is the sample size, which we know is equal to 5. The confidence coefficient is actually the t value in our formula, and this is the value that we need to get from the table that we talked about in the previous video. So knowing that we have chosen a 90% confidence level and that our sample size is equal to 5, which means that our degrees of freedom is equal to 4, then this means that the t-value that we are looking for is equal to 2.132, and this is the confidence coefficient that we need to insert in the formula or in the Excel sheet and to calculate the margin of error. So this is the value we got here, and then using the formula that we already know by now, we are going to calculate the margin error. So as you can see, the margin error turns out to be equals to 6.89 versus a mean that is equal to 10.6. So if we need to calculate the lower bound and the upper bound of our confidence interval, this means that we will need to subtract the margin error from our mean and then add it. So as you can see, our lower bound is equal to 3.7 and our upper bound is equal to 17.49, which means that this is actually quite a big range. So this means that our mean will be anywhere in between 3.7 and 17.49. So in order to have a better idea about how much our margin error is with respect to our mean, we can calculate it as a percentage. As you can see, the percent of the mean is equal to 0.65 or 65%, which means, in other words, that our confidence interval is going to range anywhere less or greater than the mean by 65%, which is definitely a very big value. And what this means is that we need to increase the number of times that we run our model in order to reduce our margin of error and reach a more acceptable confidence interval. So we will repeat the experiment with different numbers of run. For example, here I specified that the model should be run for 10 times. Of course, we have to be careful regarding changing the confidence coefficient or the t-value based on the new number of runs that we have chosen. So, for example, here you see now that the mean is going to vary with 37%, which means that our confidence interval is going to be between 9.3 and 20. Then here we increase to 20 runs and we change the confidence coefficient and we get a 27% variation. So the new confidence interval is between 11.32 and 19.87. As for this one corresponds to 30 runs. And as you can see, our new confidence interval is between 11.0.4 and 16.69 with around 20% variation from the mean. So this could be an acceptable value. Of course, if you need more precision, if you need your confidence interval to be less than this or narrower than this, then in that case, you will keep increasing the number of runs until you reach the needed margin of error or the needed confidence interval. So as you can see through the example that we presented, that the general idea is that we need to progressively iterate and add the number of runs in order to reach a satisfactory confidence interval based on the confidence level that we have already chosen. So it is up to you to specify where you need to stop. So in the example that we just presented, we have reached the conclusion that we will need at least 30 runs in order to reach a confidence level of 90% with a confidence interval that only varies 20% around the mean. Now, there is an option inside the experiment that allows you to automatically go through these iterations without having to do them manually. You can find this in the replication section. So if you choose replications with varying number of replications, what you need to specify here is the minimum and the maximum number of replications that you want the simulation to try with. And of course, you will need to specify the confidence level that you want to reach regarding a certain value, which is the value that you are looking for. And the error percent is actually the value that you would want your confidence interval to vary around the mean. So if we will accept that our confidence interval will be 20% less or over the mean, this means that we will specify a zero point 0.2 error percent. Unfortunately, this feature currently doesn't work properly. So most of the times it will give you incorrect results. This is a bug in AnyLogic, but we hope that they can fix it soon because this is actually a very useful feature that would save a lot of time instead of doing these iterations manually, that you can directly find the minimum number of replications that you need to reach the confidence level that you want. In conclusion, when we need to provide answers to the questions that the stakeholder is looking for from a simulation model, we have to provide them with answers that we are quite confident of. That's why we can't give them the result of one simulation run or even one mean, because we can't risk giving them a completely wrong value. This is why a very good approach would be to use these confidence intervals. We can even use the t-distribution graphs to graphically convey the results. In our case, for example, we can use the t-distribution graph with 29 degrees of freedom relevant to our 30 runs that we decided to stop at. So this is how the t-distribution graph looks. Now, usually 68% of the data belong one standard deviation away from the mean, which would be this area, because here we have the one standard deviation, and 95% of the data will belong two standard deviation away from the mean, which in this case would be this area. So in our case, since we have reached a 90% confidence level, then it is going to belong somewhere here. So these are the limits that will correspond to our lower bound and upper bound of the confidence interval. So what we can explain to the stakeholder is that 90% of the time, the number of people that are going to leave the system are between 11 and 17.